Welcome to the new era of video creation with Bayozi8. This is our new series on AI teaching natural language processing. Today we will discuss the tokenization in NLP. Here are the contents. Tokenization is one of the first and most important steps in processing text for natural language processing, NLP. It involves breaking down a stream of text into smaller units known as tokens. These tokens could be words, subwords, characters, or sentences, depending on the tokenization approach used. This step is essential because NLP models like language models, parsers, and classifiers all require input data to be in a structured format. Tokenization helps prepare raw text for other tasks such as part-of-speech tagging, named entity recognition, machine translation, and text summarization. Essentially, tokenization is like cutting up a piece of text into manageable chunks that a machine can analyze and process. Tokenization can be performed at different levels. Word-level tokens. This approach splits text into individual words. For example, the sentence, "I love NLP," would be split into "I love NLP." This is the simplest and most common approach. Subword-level tokens. Instead of splitting text into whole words, this method splits words into smaller, meaningful units called subwords. For example, the word unhappiness could be split into unhappiness. Subword tokenization is useful in handling out-of-vocabulary words and is used in models like BERT and GPT. Character-level tokens, here, text is split into individual characters. For instance, the word love would become LLOVE. Character-level tokenization is useful for languages with complex morphology or tasks like language generation. Sentence-level tokens. In some cases, text is tokenized at the sentence level, breaking the document into individual sentences. This is often used in tasks like document summarization or machine translation. Tokenization is important because it allows machines to break down a continuous stream of text into meaningful, digestible units. By segmenting text into words, subwords, or characters, tokenization helps machines understand language structure. Without tokenization, a model would have to process the entire text as a single block, making it challenging to analyze individual components like words or phrases. Tokenization is essential for tasks like part-of-speech tagging, where understanding each word's role in a sentence is necessary, or machine translation, where each token corresponds to a translation unit. In short, tokenization helps break the complexity of natural language into smaller chunks that can be more easily understood and processed by NLP models. Tokenization is not a trivial task, and several challenges arise during the process. Punctuation and special characters. Determining whether punctuation marks should be treated as separate tokens or combined with surrounding words is often context-dependent. For instance, don't could be tokenized as don, kami ti, or a don't, depending on the task. Language ambiguities. Some words or phrases can be ambiguous. For example, New York should be treated as a single token, named entity, rather than two separate tokens, New and York. Similarly, contractions like isn't need to be carefully split into is, ent, or kept intact based on the task. Languages with no spaces. Languages like Chinese, Japanese, and Thai do not use spaces to separate words. Tokenization in these languages requires more advanced techniques like word segmentation, which can be challenging due to the lack of explicit boundaries. Consistency. Different tokenization strategies can produce inconsistent results, making it harder to maintain uniformity across models or applications. Tokenization strategies vary significantly between languages. In space-separated languages like English, Spanish, or French, tokenization is relatively straightforward. Words are separated by spaces, making it easy to split the text. However, even in these languages, challenges like handling punctuation, contractions, and multi-word expressions arise. In non-space-separated languages like Chinese and Japanese, tokenization is more complicated because there are no spaces to delimit words. Instead, word segmentation techniques must be employed, which often rely on dictionaries or statistical models to identify word boundaries. Multilingual tokenization introduces additional challenges, as different languages may require different approaches. For example, languages with rich morphology, e.g. Finnish, Turkish, may require splitting words into smaller units to handle grammatical variations. Tokenization methods can be broadly classified into two types. Rule-based tokenization. This approach relies on predefined sets of rules and patterns to split text into tokens. For example, rules might specify that a space separates words, or that punctuation marks are treated as separate tokens. While rule-based systems are fast and deterministic, they may struggle to handle ambiguities and complex linguistic structures. Statistical tokenization. This method uses machine learning techniques to identify token boundaries based on statistical models trained on large corpora. Statistical approaches can adapt to more complex languages and handle ambiguous cases better than rule-based systems, though they tend to be slower. Hybrid tokenization systems often combine both techniques to balance speed and flexibility. A rule-based system can handle straightforward cases, while a statistical model can be used for more complex or ambiguous situations. There are several well-known libraries available for tokenization in NLP: NLTK, Natural Language Toolkit, a comprehensive Python library for NLP that provides various tokenization methods, including word and sentence tokenizers. NLTK is highly flexible, but can be slower compared to other libraries. Spacie, a fast and efficient NLP library with pre-trained models that include built-in tokenization. Spacie is optimized for performance and is ideal for production environments where speed is important. Transformers, Hugging Face. This library provides tokenization tools specifically designed for transformer-based models like BERT, GPT, and T5. These models often use subword-level tokenization, so the tokenizers are specifically designed to handle large vocabularies and complex tokenization schemes. These tools offer pre-built functions for tokenization, which can significantly speed up development and experimentation. Subword tokenization is a powerful technique used in modern NLP models to break words down into smaller units, such as subwords or morphemes. This approach addresses the out-of-vocabulary OOV problem, where words not seen during training can be represented by combining smaller known subword units. Some common subword tokenization techniques include byte-pair encoding, BPE, a data compression algorithm adapted for NLP. It iteratively merges the most frequent pairs of characters or subwords to form new subwords. Word piece, a variant of BPE used in BERT that builds a vocabulary of subwords by maximizing the likelihood of the data. Subword tokenization is critical for transformer models because it allows them to handle a vast number of words without needing to store every single word in a fixed vocabulary. Transformer models like BERT and GPT use pre-tokenization as a part of their input processing. Pre-tokenization involves breaking the input text into smaller chunks, e.g., words or subwords, before feeding it into the model. This is crucial for consistency in token representation across various text inputs. For instance, BERT uses wordpiece to tokenize words into subwords, while GPT relies on byte-pair encoding, BPE. These techniques are designed to balance vocabulary size and the ability to handle rare or unseen words by breaking them into subword units that the model has seen during training. Let's walk through some examples of tokenization. English sentence, "Natural language processing is fun," would typically be tokenized into words like natural, language, processing, is, fun, Here, punctuation marks are often treated as separate tokens. Subword example. The word unhappiness might be split into subwords like unhappiness, using a technique like wordpiece or BPE. Chinese tokenization. For languages like Chinese, there are no spaces between words. The sentence, "Wo I zi ran yu yen chu li." I love natural language processing would be tokenized into characters or words, like wo, I, zi ran, yu yen, chu li. These examples illustrate how tokenization adapts to different languages and tokenization strategies. Tokenization is at the heart of many NLP applications. Text classification. Tokenized text is the first step in tasks like spam detection, topic classification, or sentiment analysis. Machine translation. Tokenization is used in machine translation systems, where both the source and target languages need to be tokenized for effective translation. Sentiment analysis. Tokenization allows the model to identify individual tokens, words or subwords, and understand how they contribute to the overall sentiment of the text. Information retrieval. Search engines use tokenized text to index documents and perform efficient searches based on user queries. When evaluating tokenization methods, several factors must be considered. Accuracy. The tokenization should accurately reflect the linguistic structure of the text, especially for languages with complex grammar and morphology. Speed. Tokenization must be efficient, especially when dealing with large corpora or real-time applications. Memory usage. Some tokenization methods, like those based on large subword vocabularies, can consume considerable memory. The efficiency of these methods is essential for handling large datasets. Adaptability. A good tokenization method should be flexible and adaptable to different languages, handling nuances like morphology, punctuation, and multi-word expressions effectively. The future of tokenization is exciting, with several key trends emerging. Subword tokenization evolution. Subword tokenization techniques like WordPiece and BPE will continue to evolve to handle larger and more diverse vocabularies efficiently. Context-aware tokenization. Future models may use context-aware tokenization, adjusting token boundaries based on the context in which words appear. BERT, GPT. Integration. Tokenization will remain tightly integrated with advanced models like BERT and GPT, allowing them to process and understand text better. Multilingual and code-mixed text. Tokenization methods will continue to improve to handle multilingual, code-mixed, and other non-standard text forms more effectively. In summary, tokenization is a critical process that helps break text down into manageable units. It plays a fundamental role in many NLP tasks such as text classification, sentiment analysis, and machine translation. Different tokenization strategies, such as word-level, subword-level, and character-level tokenization, can be used depending on the language and application. While tokenization has its challenges, especially when dealing with languages that don't use spaces or highly ambiguous text, modern tools and techniques have made it more efficient. Libraries like Spacy, NLTK, and Transformers are invaluable for implementing tokenization and helping researchers and developers handle the complexity of natural language.